So these are some extra problems on conversions between mass and moles and molecules or atoms and using molar mass. They were created in the fall of 2020 because this lesson plan was being done asynchronously, but these problems would be good for certainly other semesters as well. Alright, so in our first example, we're told that a sample contains 3.89 times 10 to the 26 carbon dioxide molecules. And we want to know how many moles of carbon dioxide there are. So whenever we're going from atoms or molecules to moles, we're always going to use Avogadro's number. And so Avogadro's number tells us that in 1 mole of anything, there are 6.022 times 10 to the 23rd of whatever we're talking about. In this case, it's carbon dioxide molecules. So I'll use molecules. So this is just a one-step conversion. We can go directly from molecules to moles. And so I'll start with my 3.89 times 10 to the 26 CO2 molecules. And then I want the molecules to cancel. So I'm going to put this in the denominator. And you don't have to put the CO2 label on these problems. There are some problems that we'll get to later on where it's useful to label what we're talking about specifically. Here, the only thing we can be talking about is CO2 molecules, but I'm adding that label in just for being explicit. So the CO2 molecules will cancel with the CO2 molecules. My answer will be left in moles of CO2. I get an answer to 3 significant figures of 646 moles of CO2. Alright, I was getting bored with just coming up with random numbers, and so I started wandering around my kitchen, finding things that I could weigh to make practice problems out of. So my favorite cast iron pan weighs 2.26 kilograms. So if we assume that that pan contains only iron atoms, I want to know how many moles of iron there are. And so to go from the mass of an element, or a compound for that matter, I need the molar mass. And so for just an element, I can just go to the periodic table. So this is iron, it's just an element. And so the molar mass of iron on the periodic table is 1 mole is equal to 55.85 grams of iron. All right, now you may have noticed another issue. So if I had the mass in grams, I could get to moles in just one step. But I gave you the mass in kilograms, so we need to convert from kilograms to grams before we can go from grams to moles. Now we know that conversion. We know kilo is 10 to the 3rd, so 1 kilogram, remember the 1 always goes with the side with the prefix, is equal to 10 to the 3rd grams. Alright, so I'll take my 2.26 kilograms, and then I want that kilogram to go away. So I'll put 1 kilogram on the bottom, so then 10 to the 3rd grams will go on top. My kilograms cancel. And so then I want the grams to go away, so here's my other grams. So I need to put 55.85 grams on the bottom, and then 1 mole on top. So my grams will cancel. And so I'll do 2.26 times 10 to the 3rd, divide that by 55.85, and I find that my cast iron pan contains 40.5 moles of iron. And just in case anybody yells at me, I realize that we're making an assumption that that pan only contains iron atoms, and that's not the case. Cast iron does contain small amounts of carbon, silicon, and some other elements, but it's mostly iron. Alright, in this case we want to go from moles to mass. And the compound we have is magnesium nitrate. So we're just given the name, we need to determine the formula. So we always want to ask, is it ionic, covalent, or an acid? Magnesium is a metal, nitrate is a polyatomic ion, so this is ionic. We know the charge on magnesium, it's +2. The nitrate ion is NO3 minus. So the formula of magnesium nitrate is MgNO3 2. So now we can determine the molar mass. So magnesium is 24.31 grams per mole. I have 2 nitrogens, and I have 6 oxygens. And so when I add all that up, I get 148.33 grams per mole. Of course, I like to rewrite that. I like to say that 148.33 grams is equal to 1 mole. So I can write it like my other conversion factors. Alright, and so I think I have all the information I need. So and then I want to put 1 mole in the bottom, so the moles will cancel. So the 148.33 grams will have to go on top. And I get a mass of 115 grams. Alright, so another example of me wandering around my kitchen finding stuff to determine the mass of. I grabbed an ice cube out of the fridge, and I found that it weighs 12 grams. And so I want to know a couple things. I want to know how many water molecules are in that ice cube, and then I want to know how many oxygen atoms and how many hydrogen atoms. So let's tackle the first question first. How many water molecules are there in that ice cube? So going from mass to molecules is going to be 2 steps. I have to go through moles first. So I need to get that mass into moles, and then I can go from moles to molecules. So to go from mass to moles, I need to use the molar mass. So water, of course, is H2O. So 2 hydrogens, 2 times 1.01, 1 oxygen. So that has a molar mass of 18.02 grams per mole. Or again, I like to write that as 1 mole is equal to 18.02 grams. Alright, so that'll get my 12 grams into moles, and then always to go from moles to either, whatever I'm dealing with. In this case, I have a compound, and it's a covalent compound, so I'm going to go to molecules. So it would be 1 mole equals 6.022 times 10 to the 23rd molecules, right, and that's of water. So I'll start with my 12 grams. I need the grams to go away, so I'll put my 18.02 grams on the bottom, 1 mole on top. Right, I've used this one, so I'm going to cross it out. Now I want to get rid of moles, so in my next conversion factor, I need to put 1 mole on the bottom. So 6.022. I'm just going to write molic for molecules. So my moles cancel. And so when I do 12 times 6.022 times 10 to the 23rd, divide that result by 18.02, I get 4.01 times 10 to the 23rd. And I'm going to specify, right, this is water molecules. Alright, so that's the first part of the question. How many water molecules are there? Now they also want to know how many oxygen atoms. And so this is pretty easy, right? In the formula for water, if I have 1 water molecule, I have 1 oxygen atom. So I'm going to set that up as a conversion, even though, I'm sure most of you realize we probably don't need to do that work. So I would say, okay, one H2O molecule is equal to one oxygen atom. So then I would say, okay, I've got my 4.01 times 10 to the 23rd water molecules times one water molecule is going to give me one oxygen atom. So 1 times 1, I have 4.01 times 10 to the 23rd oxygen atoms. Now, if we're doing this on a quiz or a test, you would not have to show this workout. If you recognized for every one water molecule, I have one oxygen atom, and so you just told me I had 4.01 times 10 to the 23rd oxygen atoms, that's fine. But I wanted to show it this way just because sometimes it's not this easy, and it's helpful to be able to set up this conversion. Right, and so I'll do the same thing for hydrogen atoms. Right, now you could certainly, figure out that if I have if I have one water molecule, then I have two hydrogen atoms. So I would just take the 4.01 times 10 to the 23rd and multiply it by 2 to get the hydrogen atoms. But just for the sake of completeness, I'm going to set this up as another conversion. And so I'll say, okay, one H2O molecule is going to give me two hydrogen atoms. And so if I take my 4.01 times 10 to the 23rd H2O molecules, and then one water molecule is going to give me two hydrogen atoms. Right, the water molecules cancel. So multiply by 2, divide by 1, I get 8.02 times 10 to the 23rd hydrogen atoms. All right, so one more example, and we're going to work a density example into this. So a typical shot glass holds 44 milliliters of liquid. If we assume that we filled it with pure ethanol, I want to know how many ethanol molecules it can hold. And then we're given the density of ethanol. So to get to molecules, I need to find the mass of this sample. Right? If I have the mass, they gave me the formula, so I can get the molar mass and get the moles. And if I can get the moles, then I can use Avogadro's number to get the molecules. So the first thing I have to do is get that 44 milliliters into grams. I've got to convert that volume into a mass. And so what connects volume and mass is the density that they gave me. So I know that density is mass over volume. And so whenever I have these math or algebra problems where I'm just doing multiplication and division, I always like to rearrange my equation first and then plug in the numbers. So I'm looking for the mass of this ethanol, so I need to isolate the mass, and so I need to get rid of that volume. So I'll multiply both sides by V. Right, so then mass is equal to volume times density. All right, and so now the reason I like to rearrange is because it makes the dimensional analysis easier. So I have my 44 milliliters times 0.789 grams, right? And I guess remember, a centimeter cubed is a milliliter, right? They're the same thing. Centimeter cubed is a milliliter. So if they gave me the density in 0.789 grams per centimeter cubed, they also gave me the density in 0.789 grams per milliliter. So I'm just going to say grams per milliliter. And when I multiply that out, I get 35 grams. All right, so I have the mass of ethanol. So to get the moles, I need the molar mass. So for the molar mass, I have 2 carbons, 6 hydrogens, and an oxygen. So that has a molar mass of 46.08. A molar mass of 46.08 grams per mole. Of course, I like to rewrite that as 1 mole equals 46.08 grams. And so I can use that to go from my 35 grams to moles. And then to get to molecules, I would use that 1 mole is equal to Avogadro's number of molecules. Alright, so I have my 35 grams. One mole, grams cancel. 1 mole. My moles cancel. And I get a final result of 4.6 times 10 to the 23rd molecules.